Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Mashudu Mamburu. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center and broadcast by Pakama Research and Development. Welcome once more. We're looking forward to this lesson, hoping you're going to enjoy yourself. Our lesson, we are doing the last part of matter and materials, which is polymers and electronic properties of matter. So we'll be dealing with that, hoping you will enjoy yourself. So as I said when I started to say, in paper 2, we are having 75 marks. Of those 75, we are saying 62 will come from this topic of matter and materials. So we're saying it's a lot of paper. When you write paper 2, there's a lot of marks that comes from this section. So we're hoping you're going to collect all these marks as we've been doing. So it's 75 marks for 1.5 hours. And the questions levels are broken down as you can see there. You have the recall questions, which is 30 marks. Then the understanding, which is right about 35. The analyzing, which is about 30. Then your evaluation at 5% of the paper. So that will be the structure of our paper during the prelim and during the final exam. We are saying in our paper, look forward for multiple choice questions. And we are saying look forward to either matching items or one-word items, and we spend about 16 minutes on this type of equation. Remember, we are saying for every 1 mark that you want, spend around 1.2 minutes to ensure that you collect all your marks. So don't be in a hurry when you're answering questions. You have 1.2 minutes for every mark, so spend some time there. Then you will have section B, which is structured long questions, which is about 61 marks. Then the total is 75 and 1.5 hours, as I indicated. So now let's look at plastics and polymers. Here we are dealing with only basic polymerization as application of organic chemistry. So this is what you have to know. According to the exam guideline, we are saying describe the following terms, which are macromolecule, polymer, monomer, polymerization, plastics. And then you have to identify monomers from given addition polymers, and you have to discuss the industrial uses of polyethylene. So this is your scope as far as plastics and polymers are concerned. So the most important thing is for you to remember all those definitions, which the first one we're saying is a macromolecule. The second one we're saying is a polymer. The third one we're saying is a monomer. And then the fourth one is polymerization. And then you have to know the plastic synthetic materials derived from organic compounds. So you have to know about the plastics, and you have to identify the monomers, meaning that when you're giving a polymer, which is made up of many molecules, you have to know where its origin, to say what was used to form this polymer. And then lastly, you have to discuss the industrial uses of polyethylene. So the most important thing are those definitions that I've tried to summarize for you there. I said MOP, so that you can remember all those definitions, to say these are the definitions you have to know. What is a macromolecule? The MA there for macromolecule is that a macromolecule is a molecule that consists of a large number of atoms. So the keyword there being large number of atoms. So when you say macro, you are saying this molecule is made up of a large number of atoms. So you have to remember that definition. It's an exam question. The second one is what is a polymer. So when you say a polymer, we're saying this is a large molecule. So that will be a macromolecule, a large molecule composed of smaller monomers units covalently bonded to each other in a repeating pattern. So you have to know that definition as well, to say what is a polymer. The third definition that you must know at all time, what is a monomer? We're saying a monomer, you know, mono means one. So this is small organic molecules that can be covalently bonded to each other in a repeating pattern. It means when it's a monomer, it's a small organic molecule that can be joined to other small molecules with covalent bond. You'll remember when we started organic chemistry, we indicated that we are dealing with covalent bonding, which means sharing of electrons. So we still have that here. So it's a small organic molecule that can be covalently bonded to each other in a repeating pattern. So now we look at polymerization to say what is the process itself. Polymerization is a chemical reaction in which monomer molecules join to form a polymer. So polymerization, we are joining the monomers to form a polymer. So you have to remember that, a chemical reaction in which monomer molecules join to form a polymer. So that is as well exam question. Now, under plastics, we are saying no, these are synthetic materials. They are derived from organic compounds. So when you see plastics, you must know these are organic compounds that we use to make these plastics. And we are saying be able, when we give you a polymer, a light structure, you must be able to know which monomers we use to form that polymer. And then lastly, the use of plastics. So that is the focus of our lesson for today. For the first part, remember, we're going to do the electronic properties of matter as well. Now, to say, as we move now, we look at what is referred to as polyethylene. So you will know the structure of ethene, which is ethene is eth, 2 carbons with a double bond. Hence, we are saying this is ethene. So that is the structure of ethene. So when you say poly, it means many. Many ethene. It means you are joining many ethenes to form polyethylene, which means now it says now ethene is a monomer, because we said it's a small organic molecule that are joined together using covalent bond to in a repeating pattern. Then they are able to form polymer. So our monomer is ethene. Ethene is our monomer when we form polyethylene, because it's many ethenes. So we took the name from that. So you have to understand the type of reaction. I indicated that this will be addition. Remember, we said when you see unsaturated or a double bond, you know that the type of reaction that will take place, it will be addition. But in this case, the type of addition, we call it addition polymerization. So if you can check this first a bullet there, it says when lots of ethene molecules bond together, a polymer called polyethylene is formed. So we're joining monomers, which are ethene, then they form a polymer, which is called polyethylene, because it's made up of many ethene molecules. So I hope you have understood that. We are saying that ethene is unsaturated monomer, which when joined to other ethene molecules through an addition reaction, forms the saturated polymer called polyethylene. So I have emphasized that a lot to say when you see poly, you see many. Ethene is main ethene. How did you join them together? You were using what we refer to as addition polymerization. So you have to know that the addition polymerization is when for polyethylene, when you are dealing with a polymer called polyethylene, is that we are joining many monomers. So a monomer called ethene, we are bringing another monomer, which is another ethene, and many repeating itself. Hence, we refer to it as polyethylene. So it means we are going to add a lot of these ethenes together to form a polyethylene, which is a polymer. So we're saying a polymer may be a chain of 1,000 monomers. So we can have 1,000 of these ethenes that are joined together in order to form polyethylene. So it is impossible to draw the entire polymer. Remember, if I give you 1,000 of this ethene and say draw the structure of polyethylene, it will be very difficult to write that in a book, 1,000 ethenes. Hence, now we say rather the structure of a polymer can be condensed and represented as follows. So if you can see here, you can see it's an ethene inside those brackets, and then we have N there. The N there now is standing for the number of monomers that we are having. So number of monomers, if we have 1,000 of them, N will be 1,000. So you will be able to know that this polymer, which is polyethylene, has been formed by adding together 1,000 of the ethenes. So the N is showing the number of ethenes that we're having. So it's very much important, because in the exam, we will definitely like to give you a question like that one, where you have that. So you have to know that it stands for a polymer, because that N stands for the number of ethenes that we are having. So if we were to draw the structural formula, you can see it will be a very long structural formula. Remember, after addition, you no longer have a double bond. So we're having a double bond when we're having our ethenes, but when we add them together, the double bond is broken, and you have a long chain that is made up of single bonds that is now saturated. So you can see, you usually will say this was unsaturated, it's forming saturated, and we said the reaction will call it addition. So hence we refer to it as addition polymerization. So you have to understand that we call it addition polymerization because we have the double bonds. We are adding the ethenes together to form a polyethylene. So the reaction is called addition polymerization. So I hope you've understood that part, that we start with our monomers, which is ethene, we join them together. Whichever the number that we are having, there can be 1,000 of them, they are able to form a polyethene. So that is the first part that I hope you have understood and you are moving with me. Now we are saying a polymer may contain thousands of chains of monomers, and so it is impossible to draw the entire polymer. I said that. Rather, the structure of a polymer can be condensed and represented. I showed you that statement in the previous slide. The monomer is enclosed in brackets, and then the N represents the number of repeating units, which is our monomers, to say how many monomers, saturated monomers now that do we have in the polymer, where N is a whole number. So when we say N is a whole number, we are saying you can't write N there as a half. It must be 1, 2, 3, 4, 5, because you don't have a half of an ethene. You will understand me on that. So it must be a whole number. What this shows is that monomer is repeated indefinite number of times in molecule of polyethene. So we're just repeating many ethenes. So we're having ethene repeating itself many times, as I've indicated in the previous slide. So I hope you are moving with me. You understand now how a polymer is formed. So we move. Now, what do we use these polymers for? We use this polymer industrial use, for example, for making squeeze bottle. I know you are very used to that. So squeeze bottle, plastic bags that you are getting when you go to the shops, the films, the toys, the molded object, as well as electric insulation. You will see the electric wires. They don't come naked as they are. They are insulated. We're using the plastic material there. So plastic is very much important in terms of the use. So definitely in the exam, we do ask you to give us the industrial use of polyethylene. So it's very much important that you understand how it is used, this polyethylene. It is a recycling number 4, which means that it is easy to process, has strength, toughness, flexibility, is easy to seal, and has a barrier to moisture. So what we are simply saying now here is that you could have seen many people collecting these plastics, because plastics are very good because you can be able to recycle them. So don't just throw them anyway for environmental reasons as well. So treat them wisely, put them in the right place, and be able to recycle plastics so that our environment remains clean as well. So now that is the first part of our lesson that I wanted to summarize for you. We're going to do a few questions that are based on polymers. But however, before we do the questions, I would like to do the electronic properties of matter, so that when we do questions, we just deal with questions, then we are able to complete our lesson as nice as it must be. Now, electronic properties of matter. Now, when it comes to electronic properties of matter, learners, we are talking here about a semiconductor. You know a semiconductor, you will know a good conductor. The wires that you are using at home for electricity and all that, they are good conductors of electricity. So today, our focus will be on semiconductor. So a semiconductor is a material that has electrical conductivity between that of a conductor and an insulator. So it has both properties of an insulator and properties of a conductor. So hence we call it semiconductor. Example of semiconductors is the group 4 in the periodic table, the group 4 elements there. So we have carbon, we have silicon, we have germanium, we have tin, which is the gray and the alpha tin. Now, you will remember when we started with organic chemistry, you talked to the valence to say carbon is tetravalent, means that it has 4 electrons in the outermost energy level. So if you look at carbon, it has 4 electrons in the outer energy level. All these group 4 elements, they have that quality. So I will refer to them as being tetravalent, which means they have 4 electrons in the outermost energy level. Remember, we said the carbon can only form 4 bonds because it has 4 of these electrons that are not bonded to anything. So they are lone pairs of electrons. So they have to be bonded to something so that they can be fully filled. So we're simply saying that carbon, silicon, germanium, and gray tin and alpha tin, all these 4. We are saying group 4 elements, they are tetravalent, they have 4 electrons in the outermost energy level, which means that for them to be fully filled, you must bring 4 other electrons. Remember, the electrons must be in pairs, and then as you have done that. So understand that we're having carbon, we're having silicon, all of them, they have that property. So our semiconductors, the good thing about them, group 4 elements, very good examples of semiconductors, and they were saying they have four electrons in the outermost energy level. Now we are saying there is an intrinsic semiconductor, which is now a pure semiconductor. The example being your diamond, your silicon, all these will refer to them as intrinsic because they are pure. They don't have any impurities. So these are 4 that we talked about. Remember, in carbon we're talking about diamond, silicon, germanium, and then we're talking about tin, both the gray and the alpha tin. So those we refer to them as intrinsic semiconductor. Let me refresh your memory. The first thing is, what is a semiconductor? We said it's a material that has electrical conductivity between that of a conductor and that of an insulator. It's between that of a conductor and insulator. So the key word there, it is electrical conductivity between conductor and an insulator. So we're saying semiconductor, we refer to them as intrinsic semiconductor because they are pure semiconductor. We can ask you in the exam, what is an intrinsic semiconductor? 2 ways. Pure semiconductor, we call it intrinsic semiconductor. We can ask you, what is a semiconductor? Conductor, you will be able to say its electrical conductivity is between that of a conductor and an insulator. So you have to know that at all times. Now, we're going to deal with a process today that we refer to as doping. So doping is the process of adding impurities. So listen to this one, it's very much important. We're going to add impurity. Remember, we said all these 4 examples of semiconductors, intrinsic semiconductors, which is our carbon, silicon, germanium, and tin. We said all of them, they are pure semiconductor. So we're going to impurify them in a process called doping. So doping is a process of adding impurities to intrinsic semiconductor. So we're having a pure semiconductor. We're going to bring impurities to them. We're going to make them dirty. You can ask yourself, for what reason? Because they were pure. Why do you bring impurities? So that is the focus of this lesson as far as doping is concerned. So during doping, we are bringing in impurities to intrinsic semiconductors. The elements of group 3 in the periodic table, you have group 3 and group 5 elements. Those are we refer to them as our dopants, can be used for doping. So we'll be using boron and gallium for doping in this case. So we're simply saying that we are using 4 of them: the carbon, the silicon, the germanium. Let me write them. We have silicon, we have Ge, we have tin there. So we have those 4. So we're going to bring impurities. Our impurities will be using the trivalent boron and the group 3. We say trivalent. They have 3 electrons in the outermost energy level. I will explain. And then we're going to bring the pentavalent. So which is our phosphorus now. Phosphorus now, it has 5 electrons in the outermost level. You can see now, when you look at the need, let's look at the need so that you understand this section and you enjoy it. Look at silicon, for example. It has a need of 4 electrons because we said it is tetravalent. It has 4 electrons in the outermost energy level. Now, remember, if now we bring boron, which has 3, obviously there will be a shortage of an electron. That's what we're going to discuss, to say why, when silicon needs 4 electrons, why do you bring boron with 3? Because there will be shortage. So that is the focus of what we'll be talking about. The same if you have silicon and you bring phosphorus, which is carrying 5 electrons. What is going to happen is that you are bringing 1 extra electron as well. So doping is dependent on that, to say it's either we're going to give shortage or we're going to oversupply. Remember, if you're having business, it's either if you undersupply, it might still be a strategy for your business. If I'm to talk to that as an example, to say if you are selling something but it's not overpopulated or it's not too much into the market, you tend to have many customers who want to buy your product because it's scarce, it's not easy to get. So that is example when you're using boron there, because we know silicon needs 4, but we're giving it 3. And then in terms of phosphorus, you can just oversupply what you are having because you are creating need, so that if it's example in our daily life, there can be more need of what you are supplying. So that is the 2 ways of doping. So in doping, it's either will give 3. Remember, we are dealing with tetravalent. These elements, they need 4 electrons to be fully filled, but we are not going to give them 4. We're going to come with boron that carries 3, or come with phosphorus that carries 5. So we'll see how they are going to behave. What is going to happen to that shortage, or what is going to happen to that extra electron that we are going to add as we are doing the process is doping. So this doping will be adding these impurities into this pure semiconductor. I hope you have understood that idea. The main thing I want you to understand is that all these group 4 elements, they are running short of 4 electrons to be fully filled. So they are saying, if you can give me 4 electrons, I will be fully filled. I will be certified. I won't have any problem. Now, instead of supplying all the needs, we will give boron, which is trivalent. It will bring 3. Then the need will still be there because there will still be one hole that is not filled with electrons. As well, when you bring phosphorus, we're bringing an extra electron. So we're going to look at that. So hence I'm talking to that so that you understand this is the basis of what we are doing here today, so that you understand what is happening. Because if you understand this, you will enjoy the session. So what I was saying, it has been, there are 2 groups of impurity atoms used in doping. The first one is trivalent atoms. As I indicated, trivalence means 3. I gave you example of boron, that is trivalent, which means it has 3 electrons in the outermost energy level, meaning that if you are bringing it to silicon, we'll still have shortage because the electrons are not enough. And then it's either boron, our trivalent atoms is either boron or gallium. So we have boron or gallium as our example. Now, or else we can bring what we refer to as pentavalent atoms. So penta means, remember, we just you have done your organic, you know, pente. Pent means 5. So you see that phosphorus or arsenic, we are saying these ones, they will have 5 electrons in the outermost energy level. If I can use X just to show the difference. So you have 5 electrons in the outermost energy level, or 5 valence electrons for phosphorus. For boron, you have 3. But in terms of the need of silicon, we said it has 4. So it needs 4. We are either bringing trivalent or pentavalent. So these groups of atoms, we call them impurities. So our impurities that we are going to add to our pure semiconductors is either boron or gallium, or it can be phosphorus and or arsenic. So we can use those 2. So in my case here, I'm focusing on boron and phosphorus to say you are having silicon that says I have a need for 4 electrons. However, when we are supplying it with boron that has 3, meaning that we're still going to have an empty space that is not filled because there won't be that space. And then for phosphorus, we are adding 5 electrons, 1 extra electrons, which means we'll have an electron that is not shared with any other electrons. Remember, we want all our electrons to be shared so that they become more stable. But in this case, we are bringing either less through boron, trivalent, or we are bringing 5, which is extra, which is pentavalent. Now, doped semiconductors, or also we can call them impure or extrinsic semiconductors, are semiconductors with small admixture of trivalent or pentavalent. It means when you are having a pure intrinsic semiconductor, which is that these are pure semiconductors, carbon, silicon, germanium, and tin. We said those 4, they are pure. But immediately when you bring the trivalent boron or the pentavalent phosphorus, they now become extrinsic because it's now a mixture of the pure and the impure. You get that? So immediately you're bringing the extrinsic or the impurity, then it becomes extrinsic. So I hope I explained it nicely and you are following me and we are moving together. Now, we are supposed now to discuss, we're going to discuss the N-type semiconductor, the P-type semiconductor, and the construction and working of the PN junction diode. Know the characteristics of the PN junction diode. So if I am to bring you where we are right now, I will say to you, when we started, we talked about intrinsic semiconductor, which I said these are pure semiconductor. So I don't want to lose you. I want us to move together. To say, we said we have our carbon, we have our silicon, all these we refer to them as pure, as being intrinsic. But the introduction of the trivalent boron or the pentavalent phosphorus brings extrinsic. So from intrinsic, now we have an admixture, a mixture of the pure one and the impure one. Then we talk of extrinsic. Now we're going to discuss, because now we're going to refer to one as being N-type, the other one will refer to it as P-type. Between the one that uses boron and the one that uses phosphorus, the one will refer to it as N-type, one will refer to it as P-type. I hope you are following me nicely there. Then we'll construct and that. Now let's look at the P-type and N-type semiconductors. So these semiconductors, they are either specified or classified as P-type and N-type semiconductors. So you have to understand that they can be N-type they can be N-type or P-type. So I will say to you immediately when I return after this small break, I will be able to indicate to you the P-type and the N-type semiconductors. I hope we are still together. You will join immediately after you drink the water and come back after a small break. Thank you. In 3 minutes, will be 3 minutes break. You will come back, then we can finish what is left. Thank you. Welcome back to this technical science lesson. I hope you enjoyed your break, you drank water. Now we are referring now to the p-type and the n-type semiconductors. So these semiconductors, we are saying you can classify them either as p-type or n-type. So n-type, let's start with the n-type semiconductors. In n-type semiconductors, the doping, we use the pentavalent atoms. Remember, I said example is phosphorus. So we'll have phosphorus, that is those 5 valence electrons. So we're using a pentavalent atoms. And elements such as phosphorus or arsenic is added to an intrinsic. We said intrinsic is a pure semiconductor. So we're bringing an impurity now, which is phosphorus. Now it's added to intrinsic semiconductor such as silicon. So we're having pure, which is intrinsic, is silicon. Silicon indicated its needs. It said, I need 4 electrons. However, when you supply, we bring impurity, which is phosphorus. That is carrying 5 now. You can see now that because electrons are negatively charged, we are going to have an extra charge, which is negative there. So you can see where the N is coming from to say we have extra electrons, 1 more electrons than the ones needed by silicon. So we're having an extra electron, hence we are saying N, negative. Oh, this N is that negative. Okay, so you can see that because of the extra electron, which is negatively charged, then we'll have the n-type semiconductor. So we're saying it is one in which electrons are majority charge carriers. So we have more electrons. They are negatively charged material. So you know the n-type semiconductors, they are negatively charged. We're saying is we use phosphorus or arsenic are used as dopants. So we call them dopants. Each of them has 5 outer electrons so that they are out of place when they get into the silicon lattice. So you can see we have the silicon structure, which I'm going to show you in a second, in a minute. We have a silicon structure. We're going to dope it. We're going to introduce this impurity, which is phosphorus, and then we'll get what is referred to as n-type semiconductor. So we are saying the 5th electron, the extra, remember it's 4 that are needed. The 5th one, electron, has nothing to bond to. You see, slowly that electron, other 4 will be able to bond to the molecule of silicon, but that other one, it won't have anything to bond to. So therefore, it's going to be free to move around. It only takes a small quantity of the impurity to create enough free electrons to allow an electric current to flow. So now, electric current is going to flow because of that extra electron that we are having. Remember, when you are doing your doping, you want electrons to flow. You want current to flow. In order for current to flow, hence we are bringing an extra electron so that now you can be able to induce the flow of current. Now, free moving electrons created as an n-type doping. So now this will become n-type because of the free moving electrons that we have. I hope you got that, but I have a diagram here that I'm going to show you now that is going to show you the free moving electrons created as a result of the n-type doping. Look at the left. We can even refer to it as a leftover electron. Is only loosely bound. So that electron that is alone. Here, a nice structure, a lattice structure. You can see the silicon as a molecule. Silicon is, they're joined together. But you can see in the middle there, we are putting in phosphorus, which is bringing 5 electrons instead of the 4 needed by all these silicons in the silicon lattice. So you can see now we are having free moving electron, which is highlighted there in red. You can see the free moving electron. That is the electron now that is going to ensure that there is conduction of electricity. Current will be able to flow because we are having that extra electron. So we are saying n-type semiconductor has conduction electrons. No holes apart from the few intrinsic holes. N-type silicon is a good conductor. Because why is it a good conductor? Because remember, silicon was having 4 holes to say these holes are empty. They want electrons to be filled. We brought 5. So all the holes that didn't have electrons, they are now filled with electrons. But we have an extra electron that will ensure that there is flow of current. That's why we're saying n-type or negative type silicon is a good conductor. So immediately when you bring phosphorus, you have made a good conductor, and that is our doping. So we call that n-type doping. Remember, for doping to occur, we had our pure silicon that we're having semiconductor. We said our pure semiconductor, which is silicon, it had a need of 4 electrons. However, we're able to supply with 5 from phosphorus. So you have to not forget that. Okay, we had silicon, we brought 5, which is extra, which is more. Silicon needed 4. That extra electron is the one that is responsible for the conduction. So it becomes a good conductor because it has the negative charge, which is our electron, that will be able to flow. So we have shown in the diagram now there to say this is how the n-type semiconductor works after the doping. You can see now we are showing you the electrons. You are having your electrons, and then as I indicated that all the holes will be filled with the electrons, and because all the holes are filled with the electrons, then we'll have electron being the one that is flowing. So we'll have flow of electrons. Remember that extra electron is the one that is ensuring that there is flow of electrons, which means if we brought to silicon, if we brought another tetravalent, all the holes are going to be filled. We're not going to have conduction because the number of electrons will be equal. But now, because the need was 4, we've brought 5. The extra electron is responsible for the conduction. Hence, we are going to have electrons flowing around this n-type semiconductor. I hope you were able to understand that. And I'm indicating as well now to say electrons have a negative charge. Hence the name n-type. You see the n there, we're taking it from the negative charge of an electron. So I hope you understand the n-type now. To say for n-type, we'll use a pentavalent. We'll use extra electrons because n, we want an extra electron, which is negative charge. We're saying n for negative. So for us to have an n, which is negative, we brought extra electrons. Hence we use phosphorus that had 5 instead of 4 that were needed by silicon. I hope you have understood this section and you understand why now the n-type doping occurs. It occurs so that this remains a good conductor. So we have a good conductor now because it has undergoing doping. But this is the n-type. So now we're going to go and look at the p-type where we're dealing now with the positive one. So I would like to go back and I would like to go forward to the p-type. Now, when we talk to the p-type, what you have to look at now is that we still have our silicon. In fact, my diagram is even nicer than my drawings. We have silicon there. You can see all these silicons, they are looking for around here. They are looking for this one, there is a hole here. It's looking for an electron. And then these holes here have been filled. Remember boron. Silicon is looking for 4 electrons. Boron brings 3. Boron. Now you see that we are still having shortage. So what happens is that instead of n-type, remember in the n-type we had extra charge. We had extra negative charge, which was an electron that made the conduction possible. In this case, we are having a hole. Hence, we have indicated there. We are having a hole that is not filled with the electrons. So the conduction is going to happen about that hole. Hence, we are saying in this statement that in a p-type doping, trivalent, I said tri means 3. It has 3 valence electrons. Elements such as boron or gallium. So we can use boron or gallium. So they are trivalent like that, as I indicated. They are added to this pure or intrinsic semiconductor, such as silicon. So you can see, as indicated nicely in that diagram, we are bringing boron. Then when you put it there, it will leave one hole that is not filled. So we are simply saying silicon has 4 holes around it. They need to be filled with electrons because all these electrons are not paired. So there's a hole there, there's a hole. Wherever there is an electron next to it, it's a hole. So when you bring boron, you are going to fill 3 holes. Then you are remaining with 1 hole that is not filled with the electron. So what happens now? We are saying it is one which the holes are the majority carriers. They are positively charged. Remember, when you are running short of electrons, it's a positive charge there. So these holes of ours, they are positively charged. So this hole that is not having an electron is positively charged, is electron deficient, is running short of electrons. So these holes, hence we are saying because these holes are positively charged. Remember, because we have a hole and the hole is positively charged, hence with p-type. So you can see the P there is for those holes. which are positively charged. So these are positive type semiconductor. The P is showing that we have the positive, which is the one that is driving the conduction of our charge or of our electrons to flow. Now, we are saying it is one in which holes are majority carriers. They are positively charged material with p-type doping. Boron or gallium is used as the dopant. Each of them has only 3 electrons, as I indicated many times, in the outer energy levels. When mixed into the silicon lattice, when mixed the boron here, they form holes. So you can see the hole is formed in the lattice where one valence electron of silicon has no electron to bond with. Hence we said C diagram. So you are able to see it there. That this one is saying I'm still lonely here, but there is only a hole, and the hole, it brings about the positive charge. Hence we refer to this as the p-type. So it's either we are giving a lot of electrons or we are giving one electron short. In this case, when we do the p-type, we use the trivalent so that we have a shortage, and that shortage will bring about the conduction. So I hope you are understanding. When it moves to that further explanation of the p-type semiconductor, we're saying the holes are created as a result of the p-type doping. So we have the holes that were created. So you can see that we created a hole when we bring boron. Instead of having 4, boron brought 3. So you see that the absence of the electron creates the effect of a positive charge, hence the name p-type. So the p-type is because of the hole that is positively charged. Holes can conduct current. So it is the holes, it's the positive now. A hole easily accepts an electron from a neighboring atom. Look at the beauty of science. Because now this hole has no electron, electrons will start to flow because they will move from neighboring atoms to this hole, and then they will be creating holes where the electrons are coming from. Then the electrons will start to flow. You see what is happening now is that hole that is bringing about conduction. There is still a flow of electrons. Why? Because of an empty hole, electrons will be jumping from where they are to the empty hole and then creating a space, and then there will be continuous flow of current because of the hole that was created by giving 3 electrons from boron instead of 4 electrons that were expected. So it's very much important to understand how the p-type and the n-type semiconductors happen. So we are saying p-type semiconductor has mobile holes, very few mobile electrons, only the intrinsic ones. So you can see that you would be having a hole that is moving around, because when electron move from one a neighboring atom to the hole, then it creates another hole. Then you will be seeing a hole at time after another, and by that there will be conduction of electricity, of charge. There will be a current that is being formed. If I'm to move back to that slide. So I hope you are understanding the p-type versus the n-type. If I'm to conclude it nicely, to say in the p-type now we have the hole. Then what happens is that the electron will move from one hole to another. So the hole, it will be like the hole is the one that is doing the flowing. Because when you look there, you will see the hole was there, then the hole is moving, the hole is in another position, because as the electron moves from one hole to another, another hole is created. So you are able to see that is the p-type, because it's the positive, which is that hole, that is driving the conduction of electricity. So I hope you understand that. So in summary, I can say you have seen how the n-type work. We give extra electron. So that extra electron is the one that makes sure that there is a conduction of electricity, or there is flow of electrons. So in this case, we give the p-type, we give less, 1 electron less, so that we create a hole, so that the one hole remain unfilled, so that now there is conduction, because the electrons will be moving from one hole to another. So it will look like the hole is being transferred from one place to another. So I hope you've understood the difference between the p-type and the n-type semiconductor. Now, we have now what we refer to as a diode. So it's very much important that you understand that we have a diode. A diode, we're saying, is the simplest semiconductor device. So now we're talking about devices now, because we must be able to use. Why are we creating these diodes if we're not going to use them? So the simplest semiconductor device, it allows current to flow in one direction, not the other direction. So if we look, we talked about the N-type and the P-type silicon. You see for N-type, we said it's the negative one. We have introduced more electrons, the pentavalent ones. The P-type, we said we have introduced the hole by bringing the boron, that is trivalent. So you have to understand the difference there. When we say N-type, we're saying more electrons, which is phosphorus as our example. And then P-type, less electrons, which is boron as an example. So you have to know the difference. So we're saying the N-type and the P-type silicon are not very effective when used in isolation. Okay, you have created an N-type and an N-type, but we are saying in isolation they are not very effective. But when they are combined, if you can take the N-type and the P-type, you combine them together, they yield some very interesting behavior at the junction. This is used as a diode. So you can see the issue of the diode, where it's coming from. So we've created an N-type diode, created an N-type silicon and a P-type silicon. Then we're going to bring them together. Then we form a diode now. Now, how do we construct this diode? Construction and working of a PN junction diode. We're saying when you put the N-type and the P-type silicon semiconductor material together, you get a very interesting phenomenon called the PN junction. So we're going to look at that, the PN junction. That gives a diode its unique properties. So a PN junction is a combination of a P-type semiconductor with an N-type semiconductor to achieve the practical utility of both. It is formed when a P-type semiconductor is joined to an N-type. So we're going to join the two because you have seen the creation of the P-type, you have seen the creation of the N-type. So we're going to join them together. Remember, the P-type is this one, where we use boron. So we're going to take that, the P-type silicon that we're having there, and then we're going to take another one, in this case, which is yes, I just wanted to go backward. Thank you. Yeah. Now, we are saying now we're going to combine both the P and the N to form the PN junction. So the junction is a combination of a P-type semiconductor with an N-type semiconductor to achieve the practical utility of both. So we're simply saying we have the P-type on its own, we have the N-type on its own. If we bring them together, we'll even get good results. Hence, we're going to construct and use this PN junction diode. Now, it's a junction because we're joining them. The construction, we're saying, look, if we have this thing referred to as diffusion. Diffusion simply means is the movement due to difference in concentration from higher to lower concentration. So you know, if you are having more water up the hill, it will move down the hill because we have a lot of water concentrated there. So we're talking to that to say, let's look at diffusion, which is the movement due to difference in concentration from higher concentration to lower concentration. So we are saying, in the absence of electric field across the junction, holes will diffuse towards and across boundary into N-type. So here I must be slow and make sure that I don't lose you. We move together. So we are saying that these holes, remember we talked about the holes that are created in the P-type and the N-type. Remember in the N-type we had extra electron, hence they are N, they are negative. On the P-type we had the holes. So we are saying the holes will diffuse towards and across the boundary into the N-type. Remember we are having the positive here. So we are saying the positive, definitely it will be attracted to the negative, which way, remember the holes are positive and the N-type is negative. So we're saying these holes will start to diffuse from higher concentration of positive to lower concentration of positive. And N-type across the boundary to N-type and capture electrons. So remember the positive, when they move towards the N-type, the positive will capture the negative. So you know they will neutralize one another. And then electrons diffuse across boundary, fall into holes. So we have two movements here. The movement of the holes towards the electrons and the movement of the electrons towards the holes. Because when you're doing a junction, you are having the N-type, which is having extra electrons, which are negatively charged. You are having the p-type, which are having the holes, which are positive charge. So we're saying the holes will move towards the electrons, which is the n-type. The p-type will move towards the n-type, and the n-type, the electrons themselves, will move towards the hole. So that's what will happen. If from higher concentration of positives, holes moving towards the lower concentration of positive, which is towards negative. The negative as well, they will move from higher concentration of N to higher concentration of P. That's the diffusion we're talking about. To say now there will be diffusion because the positive holes would move towards less concentration of positive, which is towards the negative. And the negative electrons will move towards the holes, which is now less concentration of electrons. So I hope you have understood that through diffusion, we are going to have recombination, so they will combine of majority of these carriers. This will result in the formation of depletion region. You can see now here we've indicated for you there the depletion region to say now they will start now there in the middle, they will start to meet. They will start to meet, then they will deplete, because if now remember what made the holes positive is because there was no electrons inside. Now the fact that the electrons will get inside the holes, then there's going to be a depletion now. So we refer the region between where they meet, we refer to it as depletion region. So at the depletion region, we are going to have the holes now being filled with the electrons. Region without free charge carriers. You see, the depletion region, we're saying this is a region without free charge carriers around the boundary. The charged ions are left behind and cannot move. So you can see that there is that. And then we're saying negative ions left on the p side. Remember the p side, creating a net negative charge. Now we're saying when the holes were moving, the positives were moving towards the negatives, they were leaving the negative ions on the p side. Remember, we had the p side, the holes were moving, leaving the electrons. So they are leaving now the p side being negative, the negative ions they are left there, creating a negative charge on the p side of the junction. Positive ions are left on the n side, creating a negative positive charge on the n side of the junction. So you can see now what is happening. Because the positives are moving from the positive one, which is the p-type, they are moving the holes, they are moving towards the electrons. They leave this side being negative, they leave the negative ions this side. When the electrons are moving towards the holes, they leave this side being positive. Can you see that? Then that is what that statement is saying, to say the negative ions left on the p side, creating a net negative charge on p side of the junction. Positive ions left on the side, creating a net positive charge on the n side. So you have a net positive charge this side because electrons are moving. When electrons go, remember, we're having electrons balanced with the protons. So when electrons move, then we're remaining with the positive charge. So you have to understand that as electrons move, then the charge becomes positive. So we're saying electrons will move from negative, which is where the electrons are. They will move towards the p-type, towards the holes, and the holes will move towards the electrons. When the electrons move, they leave positive charge. When the holes, the positive charges moves towards the electrons, they will leave a negative charge. So you understand that will have a positive and a negative. This results in the formation of electric field across the junction, which prevents further diffusion. So now we will not have a further diffusion, because now we've created the junction in between there, where the positive and the negative, there is depletion in terms of positive and negative. So we only have negative this side and positive that side. So you can see that's how it works, the PN junction. Now we're saying the secret symbol of the PN junction diode. So now you can see what we've created now. We have created what we refer to as anode and cathode. I would like to believe that in grade 11 you have done the anode and the cathode, though not in much details, which is the focus of next term. where you will be dealing with the redox reactions. So you will be dealing with a lot of these anode and cathode. But you will have seen from our explanation when we said, okay, the holes, we have the positive holes here that moved that side, leaving this side anode. So you can see the anode is a negative electrode. We will talk about that in detail when you are dealing with redox reactions. But you have to know now that we have created something there. We have the anode and the cathode. You were able to create now the diode. Now you have the negative and the positive. So that will be the second symbol now of how your PN junction looks like. So PN junction, a second symbol of PN junction is that one. So if we ask you in the exam, what is the symbol of a PN junction? The second symbol is that one. So when you see that symbol, you see this is a symbol of a diode. I hope you have seen how the PN junction was created and how it works. So it's very much important. So the most important one we have formed, you have seen how we formed the P junction and the N junction. Remember, for the N junction, we started with the N junction nicely. For the N type of semiconductor, we introduced extra electrons, and then for the positive, we ensured that with through boron we introduce. So we were able to have our N-type silicon and our P-type silicon. For the N-type, we introduce many electrons, hence it's N for negative, because we have a lot of electrons there. So I hope you're following that one. And we are saying for the P-type, we've used boron as our example, and because of that, it created a hole. And we are saying that hole of the electron, because silicon needed 4, but we brought 3 electrons. That hole is positively charged. Hence, we are saying it is this positive now that we get the name P. It's P-type because this is a positive type. You get that. Then we said these are conductors. However, when you bring them together, the P, the N, and the P, you are able to form what is a PN junction diode, which will work even much better, good together. So you see, teamwork is very much important here as well, because even the P and the N type, they are able to come together. We created the junction. You saw how the junction was created. We said from the P side, the positive holes will move towards the electrons. When they move towards the electrons, we said they are leaving a negative charge there. Then hence we'll be having our anode and our cathode, because when the electrons move there, the holes move there, then we have electrons that are moving from the N, the negative ones, they are moving to that side. Then when the electrons move that side, they are leaving a positive charge. So you can see on this side of the junction, we have negatives, we have a negative there. On this side of the junction, we have a positive. Then you are able to look at it and say, okay, by bringing the P and the N junction diode together, we nicely created our positive charge and our negative charge, like you will have in a normal battery that you are having, because it will have its negative and its positive. So you can see in that I even indicated there that you have the holes, you have the free electrons, you have the negative ion, you have the positive ion. So you can see you are having negative ions that side and you are having positive ions that side. So you have the anode, which is a negative one, the cathode, which is your positive one. So you are able to say, okay, we're able to create our PN junction. And how does it work? It works when the holes, positively charged holes, they move towards the negative electrons. And when the electrons moves towards the positive holes, what happens is that they are going to have a depletion region in between. By so doing, we create a negative, we leave behind a negative charged P junction, and then P semiconductor and N semiconductor that is positively charged. So you will see that we have negative charge this side and the positive. And we are saying the circuit that we use for the PN junction is the anode and the cathode. So you must be able to understand where we have that long line there. That's our cathode side, and then this side at the back of that. That is our anode. So you must know how to draw the secret symbol, obviously, of the PN junction. Now we try to further simplify the diagram of the formation of depletion region in a PN junction. So you can see now we ensured that at least we show what is really happening here. So you can see now we're having the P type which had holes. Don't forget the holes, negatively charged, and on the N type we said we're having electrons, which we indicated the electrons in that region. Then with the movement, then leaving this side, you can see we've shown only negative this side. You can see all these, they are negative, but this side they are positive. So hence we are saying now on the P type we'll have a negative charge. The net ions there, it will be negative charge, and the net ions there, it will be positive charge. That is when we're creating our anode and our cathode. Then in a second form, the PN junction, we're saying you can be able to show the PN junction by utilizing that structure. I hope you have understood there and you are moving together with me and you are enjoying the lesson. Now, you can see now in between there, we have shown what is referred to as the depletion region. So you can see we have that region there, which is our depletion region there, as we indicated. So we have shown for you that you will have the anode because it's negative that side, and the cathode is positive that side. What made this to be negative or to be positive was saying when the holes, when the holes were moving, the positive holes, when they were moving towards the electrons and the electrons moving there, they were now able to leave. When positive leaves, this remain negative. When electrons move that side, then this remain positive. So you can see where the negative and the positive is really coming from. And this will work even much better than the P and the N type are working alone. So it's very much important that we are able to do that. So I will be going to activities. I hope you have understood and you have moved with me up to now, and we are moving together. So from here we'll be doing activities. I'm hoping you're going to enjoy as well the activities, just to see and check how these questions are going to be asked in your exams. I hope now you are seeing these junctions. Now, I took this from activity 1. I took it from June 2019 question papers because we wanted you to be able to do this activity and see. Now you will see my focus is going to be on polymers, plastics and polymers. However, it's important as well because we're having this diagram to say, remember strategies on answering this question. This was the question 2 of 2019 supplementary exam, the June exams. Now, we are saying immediately when you open question 2 and you find a table like this, it says A to F in the table below represent 6 organic molecules from different functional groups. Immediately when you say functional group, you must know the definition. What is a functional group? That is the important thing. So before you even ask yourself, you must ask yourself, what is a functional group? So you're able to say, okay, a functional group is an atom. It's a group of atoms. A functional group is an atom, group of atoms that determines the chemistry. That determines the chemistry of organic molecules. So chemistry of organic molecules are determined by this atom or group of atoms. So you have to know that definition of functional group to say it's an atom. It's a group of atoms that determines the chemistry of organic molecules. So that is the first thing that you will ask yourself. Because what we are emphasizing when you get questions, analyze and understand them before you even start to answer questions. Now, you will given structure number A there, which is C5H12. You will know that 5, remember, we said is a map BPH. That's what you do. you do up to 6 carbons. So we're saying when it's 1 carbon, it's a meth. When it's 2 carbons, it's eth. When it's 3 carbons, it's prop. When it's 4 carbons, it's but. Pent, and then hex. We do up to hex. And then because we have the maximum, you can see from the general formula CnH2n plus 2, you can see that C5H12 will be an alkane because you are having 5 there. Then you know that 5 times 2, it will have been 10 plus 2 from the general formula. Remember, general formula for alkanes is CnH2n plus 2. So you are able to check, okay, N is the number of carbons. So you say, okay, N was 5, so that is C5. 2 times 5 is 10 plus 2 is 12. So you know this is an alkane. So alkane with 5 carbons is pent. So you will put "ane" there, the suffix. Remember, all these, we said these are the prefix. From the homologous series alkane, you take the name ending alkane, the "ane", then it becomes pentane. So you're able to say, okay, this is pentane. You wrote its general formula. I think I emphasized that remember, when you're dealing with this table, there are these things that you must always know. I will say, I will put it like this. I will put it like this to say F.H. Jameson as a strategy for seeing this table in question 2. To say, when you see this table, you must know that you must find the functional group. What is the functional group? So already you indicated that these are single bonds, carbon-carbon single bond. This must be alkanes. When you know the functional group, it tells you homologous series. So because it's the functional group here is a carbon-carbon single bond. So you say, this is a homologous series is alkane. So already you know homologous series is alkane. Then you ask yourself, what is the general formula? General formula is CnH2n plus 2. Then you are saying to yourself, what is the molecular formula? Molecular formula is given is C5H12. What is the structural formula? Structural formula, remember, we are saying draw all the bonds around a carbon. So you must be able to say, okay, because it's 5 carbons, you will draw the 5 carbons. If I can try, and then draw those 5 carbons there, because it's C5. And then H12 simply means that you will write 12 hydrogens around there. Then you are able to get your question with no problem. I'm just recapping for you to say now this is a C5H12. So that is the structural formula. And then the next question will be saying, what type of isomers can this structure have? You will know it will definitely have structural isomers, chain isomers. Remember, we said there are 3 types that we focus on in grade 12. We said it's chain isomers, it's positional isomers, and functional isomers. So you have to ask yourself that question to say, does this structure have isomers? Yes, definitely. It can have an isomer, which will be chain isomers. Now, lastly, what is the name? We said name because it's pentane. So you see, with that strategy, you will be able to answer all the questions, because before we even ask you any question, you will be able to say, okay, F.H. Jameson. So I must know what is the functional group, what is the homologous series, what is the general formula, what is the molecular formula, what is the molecular formula, what is the structural formula, what is isomers, what are the isomers, what is the name. So all our questions comes from there. So if you definitely asking yourself F.H. Jameson, when you see a table like that, you are gone. Where, for example, if you are to apply it here, you will say the functional group, it's a triple bond, so it must be alkenes. Yeah. So that is the homologous series. Triple bond, this is the functional group. It's a carbon-carbon triple bond. So it's an alkyne. Alkyne, remember alkene is for double bond. When it's triple bond, it's alkyne. So you know that these are alkynes. They are alkynes. And you know that the alkynes, their general formula is CnH2n minus 2. Remember, when you move from CnH2n plus 2, you remove 2, it becomes an alkene. When you further remove 2 hydrogens, an alkene becomes an alkyne. So you know that alkyne, that will be the general formula. This is the molecular formula of that functional group. And then you go like that. So it becomes easier for you to answer all the questions. If you look at number C, for example, you will say, what is the functional group? Or you can see is that bromo. A functional group is what makes it different from others. So you can see that bromo is the one that is bringing. So you are able to say, okay, so this is a haloalkane. The haloalkane. So why? Because it has a halogen there. That halogen makes it a haloalkane. So you know that you have now your homologous series. Now your homologous series being haloalkanes. General formula for haloalkanes. Remember, you just write all these. They come where we are saying you had CN, H2N. You removed one hydrogen. You put the Br. So it will be CnH2n plus 1 Br. So that's how you will go about doing that. That is the general formula. The molecular formula was given. This structure, does it have, that is the structural formula. Does it have isomers? Yes. Isomers? Yes. Positional isomers. You can take bromine to carbon number 1. Remember? Then instead of being 2-bromo-butane, if you take bromine to carbon number 1, it will become 1-bromo-butane. So it's important to say it has an isomer, and its isomer will be positional isomer. Now, when you move forward, you're able to say, okay, let me look at number D. So you apply the same strategy, AFH Jameson. You're saying, okay, let me look at it now. What do I have? I'm having what is the functional group? It's a carbon-carbon double bonds. Oh, you know, homologous series must be alkene. Sorry, because of that carbon-carbon double bond, you know this is an alkene. It's an alkene. That is the homologous series. The general formula for alkenes, you know, we remove 2 hydrogens, is CnH2n. So you're able to do that, to say, oh, this is CnH2n, and then you say, what is the molecular formula? Remember molecular formula? You're just telling us how many carbons, how many hydrogens, all the atoms together. So you simply say the molecular formula for this will be C. How many carbons do you have? 1, 2, 3. So it's C3. How many hydrogens do you have? 1, 2, 3, 4, 5, 6. So you say C3H6. That will be the molecular formula. From molecular formula, structural formula is what you are given. Isomers. Do you have any isomer? You can say, where if I take a double bond to this carbon, it will remain propene. It will remain propene. So this is not going to have your isomers. So you just say no isomers. Then you say the name is 1, 2, 3. You come here. You said it's prop. The double bond is in carbon number 1. And you see for propene, the double bond is always in carbon number 1. So you are able to say, this is propene. Even if you don't say prop 1E, because the double bond will always be in carbon number 1. So it's propene. So you were able to use the FH Jameson, and you are answering all the questions, because this is what we want you to be doing all the time. Now we finally arrived where we were going. Remember, we are dealing today with plastics and polymers. So I'm simply saying you won't be having a special questions that is dealing with plastics and polymers. They will be embedded in your question 2, sometimes in your question 4, depending on the examiners for that particular year. So it's important for you to be able to identify these polymers when you see them. Already, you can see now we are given the end there. I told you that when you see that, you know it's a polymer. It's a polyethylene because it's many. That N, we said, it can even be thousands of these monomers that are joined together. So molecule E represents the polyethylene. Define the term monomer. So we did the definition immediately when we start. Write down the name of the reaction that results in the formation of the polyethylene. The name of the reaction. Remember, I said carbon-carbon double bond. When you see unsaturated becoming saturated, because you can see on this polymer that this structure is saturated, meaning there are no double bonds between carbon atoms. So you know that, okay, we're coming from unsaturated, which is ethene, which is C double bond C with the H there and another H. So we have our 4 hydrogens that we were having there. So you can see that, okay, we were moving from unsaturated to saturated. The reaction must be addition. But remember, this addition differs from the other additions we did, because this is called addition polymerization, because we are forming a polymer. So this type of addition, we'll refer to it as addition polymerization. Then they say draw the structure of a monomer, which is what I have done for you. So let me, without wasting of time, so you will be able as well to do that. You will be able to answer all these questions and collect. This was a question paper in 2019. Remember what we said in terms of monomers? We said these are small organic molecules that are covalently bonded together in a repeating format. So we are having one of them added to another one, added to another one, added to another one. Then you are able to remember, oh, this is our monomers that are in repeating pattern. So we're saying these are small organic molecule monomers. They are small organic molecules. They are not just joined together. They are covalently. Remember, covalent bond. We said is the sharing of electrons. So they are covalently joined together. Covalently joined together. They are covalently joined together in repeating patterns. So we're having many of them joined together. So if you just look at that, you're able to answer, these are small organic molecules that are covalently joined together in a repeating pattern. Oh, you get your 2 marks. Write down the name of the reaction that results in the formation of the polyethylene. We said it's in addition, but this addition is polymerization. So when you are writing the answer for question 2.3.2, that says write down the name of the reaction that results in the formation of polyethylene. You can't be saying addition. We usually during marking will put addition in bracket to say yes, it's addition, but the main answer we want is polymerization. So if you mention addition without polymerization, you won't get it correct. But if you mention polymerization without addition, you will get the answer correct. I hope I clarified that, so that when you are writing what type of reaction, you will say polymerization, or you will be specific and say addition, polymerization. Now draw the structure of the monomer. You know most is polyethylene, so you will definitely draw your 2 carbons. This is the monomer, because the monomer must have a double bond, because it must undergo addition. And you know that for addition to take place, there must be a double bond there. There must be a multiple bond, because we add when there is a multiple bonds between carbon atoms. Yes. I hope you have understood that question and you have enjoyed it. So I just wanted to remind you of our answers. To say this as the first question was define the term monomer. We said small organic molecules that can be covalently bonded to each other in a repeating pattern. Then you are able to get your 2 marks. We can't stop to emphasize to say when you are writing definitions, ensure that you use the exam guideline. That is the only document that really tells you. So you must be sitting where you are. You must be having a copy of your exam guideline 2021 for technical sciences. And when you study your definitions, you study from there. So what we are saying to you is that even for your revision program, ensure that you have that exam guideline. Tick the points as you study. Tick that now I know what is a monomer. Now I know what is a polymer. Now I know what is a macromolecule. That is the document that you must keep very close to you as you study all the definitions. Remember, most of these questions, when we do them, they will always almost start with the definition question. So it's very much important for you to ensure that you know all these definitions and you get these 2 marks that you are supposed to get for definition. Remember, this was the question paper as well. They say write down the name of the reaction that results in the formation of that. As I indicated, is addition, but it's in brackets, so we were not worried too much about addition, but we are very much worried that this must be called polymerization. Draw the structural formula. Remember, structural formula, you show all the bonds, then that will be that. So I hope you were able to do that. If we say write down the molecular formula, you will say C2H4, because molecular formula, you are showing us how many carbons, how many hydrogens. So it's very much important to read the question, because if you say draw the structural formula, sometimes you can say write down the molecular formula of the monomer of polyethylene. So don't be confused. You must know the difference between the structural formula and the molecular formula. I hope you have enjoyed that question, and when it comes in the exam, you will definitely enjoy. Now it's like these questions, they repeat themselves. Look at that one below. This is June 2021, last year. To say below the structural formula of a monomer. So you can see our monomer is given is ethene. Define the term monomer. You see now, the same definition came back. You're supposed to say again, same definition. Oh, these are small organic molecules. Small organic molecules. So it's important that you know all these definitions so that you collect all these marks. Small organic molecules that are covalently, or that can be covalently bonded together. That can be covalently are bonded together into repeating units. Yeah. So in repeating units, so there must be repeating units. So you're able to define what is a monomer. Now write down the name of the polymer formed. This is ethene, and many of them is poly. Poly means many, so the name will be polyethylene. So if it was 2021, you would have got your 3 marks there by doing that. So I hope you've understood that. Now, at least now we have a question. Last year, November, it was part of question 4. Remember, question 4 is our reactions of organic molecules. So the question was there. So you are able to see that this is now electronic properties of matter, because it's talking about semiconductors. So it's very much important that you know that semiconductors are part of our metal materials. So metal materials are incomplete without electronic properties of matter. So it's important for you to understand and look forward to getting this question. So we had 7 marks coming from electronic properties of matter in 2021 last year final exam. It says a semiconductor is a solid substance that has electrical conductivity between a conductor and an insulator. So we were very good to you here in terms of the question, because the question gave you the definition of what a semiconductor is. So we're saying a semiconductor is a solid substance that has its electrical conductivity between a conductor and an insulator. But we can change in other year. You can find that you are now asked to calculate a semiconductor. So you must be able to say it's a solid substance that has its electrical conductivity between a conductor and an insulator. The conductivity of a semiconductor can be improved by adding impurity. You will remember we call that process. We gave that process a name. We said if you remember well, we said we use silicon as our example to say, okay, let's look at silicon. It's an intrinsic, as I summarize my lesson, as we're going towards the end of the lesson. So I'm saying to you, we said we have these intrinsic semiconductors, which are pure semiconductors. We said they are group 4 elements, being carbon, being silicon, and your gray and alpha tin as well as germanium there, as we indicated, or those are the ones that we are referring to. So we said they have valency of 4, or they have 4 electrons in the outermost energy level. So now we said if now we bring an impurity, because we said they are pure, these ones, they're intrinsic, they are pure semiconductors. So intrinsic semiconductors, by definition, intrinsic semiconductors are pure semiconductors. So if we say define intrinsic semiconductors, you will say pure semiconductors. So if you're having silicon as a pure semiconductor, then we said we either will bring phosphorus with 5. So we're oversupplying phosphorus. So when you oversupply phosphorus, we'll have N-type silicon semiconductor that is formed. So it will be N-type. Why is N-type? Because of the negative extra electron that is negatively charged. So the N there is for the negative charge that comes with an extra electron from phosphorus. So what we are saying is that now this phosphorus is bringing extra. We needed 4. We are oversupplying. When we oversupply, what will happen? We'll have an N-type semiconductor. So now with our N-type semiconductor, it will be formed. And then we said, if silicon needs, let me write here, if silicon needs 4 electrons, if we use a trivalent like boron, for example, we're going to have a hole here, because remember this hole now, there is no electron. So what is going to happen is that we're going to have a hole that is positively charged, then we'll have a p-type. So you have to know that, okay, for a p-type, we have electron deficient, we are running short of electrons. But p-type, we're having an extra electron. Hence, I mean, n-type, we're having extra electron. Hence, the n-type. P-type, we're running short of an electron. We have a hole that is positive charge. And we said, for us to come with a p-n junction, our p-n junction diodes, we said we're going to bring the n-type and the p-type together, so that the positive holes can move towards the negative electrons, and the electrons can move towards the positive holes. Then we'll have what is called the depletion region be happening, and then we'll have an anode, because when the positive holes leaves the p-type, the p-type now will be left with a net charge of negative. When the electrons moves away from the negative type towards the holes, they will leave that being positive. So we said we'll have an anode and a cathode. So that summarizes everything we talked in terms of the p-n junctions and how it functions. Now, let's look at the question. The question is saying, name the process that is used to improve the conductivity of a semiconductor, as we indicated. So you will be able to answer and say, no, this is doping that we are referring to. So this is doping as a process that you are referring to. The second question was, define an intrinsic semiconductor. As I've been saying many times to yourself, to say intrinsic semiconductor is a pure semiconductor. 2 marks, just to say pure, 2 ways, pure semiconductor. 2 ways, 2 marks. So don't forget, intrinsic semiconductor, we're saying it's a pure. We say differentiate between the n-type semiconductor and the p-type semiconductor. So you said an n-type semiconductor is a semiconductor with excess of electrons with S negative charge carrier. So it has more electrons because there is over supply. We use phosphorus, which brought 5, and the silicon needed 4. So there is oversupply of electrons. So it has excess electrons, or it has a negative charge carriers. It is formed when an intrinsic semiconductor is doped with a pentavalent. So in your case here, you can even use an example to say it can happen between silicon, which is tetravalent, when it's doped with a pentavalent phosphorus, which has 5. Then we'll have n-type because we're having excess of electrons, because phosphorus is bringing extra electron as more than what is expected. Look at the p-type semiconductor there. We're saying it's a semiconductor with a positive hole. Don't forget, because we're using boron there. Boron is bringing 3. Silicon is looking for 4. So we'll have a hole. So we have a positive hole as a charge carrier. It is formed when an intrinsic semiconductor is doped with a trivalent impurity. So it's a trivalent impurity that we have used. And my learners, I want to thank you very much. I'm saying for today, this was the lesson that we had. I'm hoping you've enjoyed. And this section, when you find them in the exam papers, you're going to give us total and if they come. Continue to practice these previous question papers. Look for previous question papers, practice them, and make sure that you are ready. When prelim comes, you must be able to answer all these questions. So as far as matter and materials, we're saying go and practice and make sure that you are ready for the coming exams. I think until we meet again, I would like to thank you and encourage you to continue with your revision and enjoy the rest of the day. I hope you have understood everything. Thank you very much.